Okay, so get me again. um, uh, an interesting challenge, I think. So what we've gone for here is to really sort of try and go back to the basics. So many of you will understand a lot of this, but what we want to do is get everybody on the same page. I was going to say the same wavelength, but that might be a bit of a pun. Okay, onto the same starting point. But I also, what I hope to do with the lecture, which will be biased towards satellite sensing, is just illustrate some of the points that through the 3 days we really maybe need to explore and think about in greater detail. And depending on your perspective, depending where you come from, you will have a bit of the problem you've tended to focus on. And what I want to do in this lecture is encourage you to think about the other things you don't always think about and ask yourself the question, does it matter for me now? Will I need to know about it in the future? Okay, so this is very much a sort of starting point lecture. So what I'm going to try and talk about a little bit is from a sort of physics perspective. If you don't like equations, don't worry, I won't have too many of them, but I will always try to illustrate those equations with some basic points. I've also tried to simplify some of the thinking, perhaps oversimplify in some places, but I find it helps understanding. So trying to give some insights into what is hopefully becoming a familiar problem and challenge. I want to recall some of the key aspects that guide LST determination, and the later lectures, Agnieszka and Mike, Adam will go into these in much more detail, so I'm really laying a foundation here. But also I thought it was important to consider some of the challenges for the next years, because in any workshop that's about learning and discovery, we want to be thinking already about the next steps beyond what we can already do. And in some cases, that might be unlocking the barriers that we currently find. Okay, this is where science becomes exciting, doesn't it? So I want to start with this picture. I will try to do the very dangerous thing. Maybe let's see if let's try that. Okay, good. Yeah, good, excellent. I hope this appears online, but if not. So one of the points about remote sensing in general and thermal remote sensing as well is that what we use for remote sensing is in itself an opportunity that's afforded by the very radiation environment, in the electromagnetic radiation environment, clearly not particle radiation, electromagnetic radiation environment of the Earth. The whole existence of the Earth, its current form, depends on the interactions of these radiations. And it's actually the other way around. We're using that principle in order to discover things about the Earth system. And that's very good because it gives us some insight. The other thing I would say is, and largely, sorry, I should say, I'm going to talk about that top of the atmosphere perspective. But what I can also say is that, you know, when we're down here at the surface, when we're trying to think about this interaction here, this is also telling us about what drives the surface and how the surface drives the nearest layers of atmosphere above. Okay, and in fact, although again, I won't go to this lecture, but you can think about the principles. It's actually telling us about the environments in which we all live, if you want to come right down to the surface. So those very principles of heat exchange and radiation actually matter here as well. So on the left-hand, so I'll spend a little bit of time, and then some of the other slides I won't need to spend so much time. So on the left-hand side is the bit that really doesn't usually concern us in the thermal infrared, but we just want to think about it for a minute. So, you know, basically we know that sunlight heats the Earth system. You'll have seen hopefully diagrams like this before. A certain amount of the radiation is absorbed or scattered in the atmosphere. The absorptive part is important, and a certain amount is also absorbed at the surface. And it's the absorption parts of this that actually matter for us, because what they do is they drive the temperature, particularly in the daytime. Okay? So at night time, we don't have the solar radiation. Again, already we're starting to think a bit about our thermal physics. We can measure in day and night, but the temperatures we observe are very different, potentially in day or night. Not as extreme as other planets, but very different. So it matters to us, actually, whether we're in day or night. So the sunlight part over there already matters. And then over here, we have this weird thing called the thermal infrared. I mean, actually, that extends right out into the microwave. And here you see the arrows actually all start at the bottom. So sorry, the bottom is a bit difficult to see, but you can imagine that you're starting at the surface and everything is being emitted upwards, and its passage through the Earth is being changed. And if you look at just some ideas of the energy, this is just the energy, you'll see that, you know, quite a lot of it is modulated by these terms here, which is net emission by greenhouse gas and clouds. And what that tells us is that if we're not close to the surface, we instantly have to worry about the atmosphere. And indeed, even when we're measuring the surface, we might have to worry about the atmosphere above us. There's a lot of radiation washing around, and it does some weird things to the signals that we see. So, kind of some of the interest part of this presentation, I hope, is in just sort of thinking about how you think about those processes and how you might explain them to other people. Okay, so just to summarise a few things, if we bring it down to parameters that we might see and contrast between the two. So we're obviously going to concentrate on this infrared part, but just to make some analogies. So in the visible shortwave, the bit that we see, when we look at that diagram, what we care about in simplicity is the albedo of the surface, the reflectivity of the surface, which is a function of wavelength. We care about aerosols and clouds, and we care about trace gases in the atmosphere. In the visible part, that might be ozone, for example. In the infrared, in contrast, we have some similar things and some slight differences. So in the arguably in the optical, the reflectivity, although it's complicated, that albedo term, controls everything we need to know about the surface from a remote sensing point of view. It's quite complex, it's got structure, geometry, but it's almost tied up in that. Whereas in the infrared, we're instantly into at least two parameters: the emissivity, so the property of the surface that is related to the material, and the temperature of the surface itself. And that's what you'd expect. I want to make one point so although we have this albedo and emissivity, both surface properties and function of wavelength, they're not related to each other unless you're right at the same wavelength. So if you're talking about reflectivity of the surface of the material and emissivity at the same wavelength, then you can actually write equations that relate those two. If you're talking about visible wavelength and infrared emissivity, so visible reflectivity and infrared emissivity, they might be related, but that relies on an underlying knowledge of the spectroscopy, we'll call it, the wavelength properties of the material. And you can make those associations, and people do, but there's certain difficulties in doing it. And through this workshop, you might see some of that. So just to give one concrete example, if you look at vegetation, people often use vegetation as a measure of the state of condition of the surface, which you can translate to emissivity in the infrared. And that sort of works, but the scatter in it is because actually it's not a one-to-one. So it depends on the crop type and the material type and the underlying soil. And they have different relationships between their optical properties and their infrared. So you have to be very careful about that. Again, you see some commonalities in the atmosphere, clouds and aerosols and gases, but actually, unlike here, we also have to care about atmospheric temperature. So the temperature profile of the atmosphere can do some weird things for you, particularly if you're in space, but also if you're in aircraft or even drones. Okay. So as I mentioned, the foundation for us is, just to take it back to instrumentation for a bit. I'm not going to say too much, but I'll try to comment a little bit as we go along about instrumentation. So remembering that we're talking about here starting from high quality instrumentation. And these sort of characteristics are very simply written down here. I think you can use to think about any remote sensing instrument. This is about satellite, but it's not the only thing. So basically, first of all, we need a source, thermal infrared. We're lucky. We have our own Earth to give us a signal. That actually matters. You go and study other planets, it's not the same because they're not at the same temperature. We'll comment a little bit on that sort of property. And even in our own planet, if we go to the poles, we start to get very cold and we start to worry about signal to noise. So it's not a panacea for everything. But we have a source. We then need to collect that radiation. So the first thing I always ask any instrument that I see, including ones out there, is okay, what's the field of view of this instrument? How does it scan? What part of the apparent image am I actually really looking at? And so, questions of resolution, questions of smoothing, all those things come into it. What am I actually measuring? Now today, I've concentrated, but I will show you a couple of pictures that lead you to other things, concentrating on radiometers, so things that have particular channels and bands, and that's the most common bit of thermal remote sensing. But quite a lot of our team here in Leicester and in NCOs in general work on spectrometers, so things that actually measure the whole wavelength dependence in the thermal infrared and measure the atmosphere as well as the surface. And we don't use those from space that much for thermal sensing because they don't have the spatial resolution. However, one of those challenges, which again, now to come to our first challenge that I'm putting out there for future years, is how we make those systems work together, from a satellite perspective. But it could be true in the ground as well. So do we need to have some spectral resolving instruments as well as our radiometry instruments if you're on the ground? It's going to be a bit tricky from a drone. you can do it on an aircraft. On an aircraft, we can fly both a spectrometer and a radiometer. And the reason for that is those spectrometers help you to give you information in the atmosphere, but they also help you to test this temperature emissivity conundrum, this separation that you're trying to achieve. You need some detectors. The quality of detectors ultimately really do influence the quality of data that you're going to get out. We typically use mercury, cadmium telluride in mid-infrared. And then calibration, so it's right at the bottom, which means it's fallen off most people's viewpoint, which is about where calibration ranks quite often. If you talk to Dave, calibration is the only thing that matters. I'm not sure you disagree with that. So absolutely vital. So for example, on this ATSR instrument, these two little boxes here, I'll use my laser pointer, it's still there, these two little things here are black bodies, so perfectly emitting infrared radiation sources whose temperature we know really accurately. One at a warm end, not what it is, about 320, one at the cold end, 280 or so. Which we in every scan we actually get a black body measurement. The other thing that's interesting about this is the other challenge we always have here, and to think about, this is where Jennifer's work and others, really interesting about the 3D representation of temperature and emissivity. In the ATSRs, we do different, and indeed the sea and land surface temperature radiometers, we do two different angles, but that's primarily to get rid of the atmosphere. And when we come to the land, as opposed to the sea, that's not actually something we can fully use at the current time, but we'd like to. Just from a satellite point of view, but again, it measures from your aircraft or wherever, is what coverage can you achieve, so what swath and things like that. So I won't dwell on that, but just to remind you that there's always a penalty, is perhaps the way to do it. Sometimes you can get really high performance, but you can't measure everywhere that you want to measure at every time. And that's in temperature, that is one of the other challenges. So remember we said one about linking instruments at different scales. Second challenge is linking measurements, particularly at different times and places, but time. Temperature is the dynamic quantity, and that is the fun of it, and that's also the challenge of it. So to come specifically a bit more to channels, so here is a spectrum, okay, and we have instruments now flying in space. We have lab instruments here that can measure spectra for you in the lab. We have instruments out that can measure on the ground, but the real beauty is to fly these instruments in space. This is a very old, low spectral resolution. I'll show you a high spectral resolution picture in a minute. But now with atmospheric spectrometers, you can measure 30, 40 trace gases that are present in our atmosphere that affect the infrared signal. But for within that, the key thing, and this is the transmission. So one means that they're highly transmissive. We can see through to the top. Zeros down here. Notice they're quite large parts of the spectrum. Here is a water vapor band. You'll see the transmission here, and I'll describe that later as 0, just to give you a feel. We can't see the surface at all at those wavelengths. Okay, so we need to choose our channels to fit in with that. You'll see that if you are used to classical remote sensing for temperature, you'll see your pretty typical 10, 11, 12 micron bands. Those are present pretty much in every instrument, particularly for land. But actually over here, you'll see one at 3.7 microns. And over the ocean, we use these channels as well for 3.7 micron. Another channel is whether we can actually bring into, there's another one around here, around 8 microns that people use in satellite temperature sensing. Can we use these other channels to get us more information? And one of the prizes of this is if we want to get emissivity and temperature, we need more than 2 channels usually. Certainly from space and certainly from planes. Typically in the design missions we're doing now, we're going up to 5 channels. So that is one of the challenge we have here. If we can get here, over here, you're starting to see commercial satellites come in. So Satellite View had an instrument called HotSat-1, a mission called HotSat-1, which is entirely based here. And you can get spatial resolutions of a few meters of that. So there's some signal to noise battles that you can win out here, but we know much less about this region in terms of its emissivity properties. So there's a challenge in how we use this really very high spatial resolution data, which is not really there necessarily for science, but can we use it for our purposes? And we did study with ESA quite some time ago, about 10 years ago, identifying this as one of the unexplored wavelength regions that we could use for both temperature and the atmosphere. Good. Right, so let's get now a little bit into more details of passive thermal sensing. So hopefully already, if you didn't already know, you've got some of the basics that we want to look at. So already by showing you a spectral picture and by talking about channels, you've got the impression, I hope, that we need to use wavelength. We need to care about wavelength. That's both at the surface and at the atmosphere. We need to care about temperature and emissivity, but then we have to worry about this attenuation of the atmosphere. Typically, at the sort of thermal infrared wavelengths we work out again in 10 to 12 microns, we don't have to worry too much about scattering. Okay, scattering in the atmosphere. We might have to worry about scattering at the surface in geometry. Okay, I won't go into that too much, but not in the atmosphere. If we go out to these 3.7 channels out there, where you actually also got a component from scattered sunlight, you might have to worry about scattering, etc. So we're not going to deal with that today, but that's a challenge for the future. So where does our signal come from? I think I'm going to actually show you a picture first. So over here in this corner here, you can see what every budding physicist learns at an early stage, which is there's a wonderful thing called the Planck function. And basically it says that if you have a body that has a temperature, it will emit radiation. And the only thing that controls that radiation is effectively the material and its structure. But you can actually build in the lab, and we can fly them in space, things that we call black bodies, which are perfectly emitting sources of radiation. So in other words, their emissivity, the fraction of its temperature radiation that it should emit, is 1 everywhere. Okay, every wavelength you've designed it for. You can actually get special black paint that does this for you. You can design in the internals of the source so it does multiple reflections, so effectively the radiation being absorbed, re-emitted, so that what finally emerges from the source is absolutely calculatable by this equation, which I'll go back to in a minute. If you look at this picture, sorry, maybe I should have changed the colours on this, but sorry about this. It's a bit slightly indistinct, but effectively this is wavelength. If you work in wave numbers, which we'll come back to later on, then this is about 1,000 wave numbers. But you can see here temperature. This is getting all the way up to sun temperatures, and you can see that the peak of this Planck function shifts as the temperature increases. And so although you can see some of that at every wavelength, in practice, you really are dominated by how this curve is moving in terms of the temperature of bodies. So if you go to other planets or look at other stars, this is really important. There are wavelengths where you just cannot see anything. Okay, so we have a unique window in some respects. The peak of the Earth Planck radiation is around 10 microns, so around 1,000 wave numbers. So around the channels we use for thermal sensing, where there are windows. So that's really quite nice. We are getting maximum sensitivity to the Earth and its radiation. Of course, the temperature does vary as that curve moves around a bit. Okay, so just to go back to the equation for a second, I won't dwell on this, but the important point is that you can write down an equation, and every physicist writes down an equation, wonders why the hell they're doing it. You know, why do I need to know this equation? It's probably the cry of every first-year physicist taking the exam in the university. And the beauty about this community is we use it every day. It's absolutely at the forefront of what we do. And you see that you can see this extreme dependence on wavelength in here. So it's got 2 wavelength dependent terms. Okay. All right. So essentially, as soon as we know the temperature of a body, we can write down. Okay. And the clue is, as soon as we know the temperature of a body, so that's not a trivial thing, right? As soon as we know the temperature of a body, we can write down the Planck function that we expect it to be emerging from that body. Now, Planck functions really are thinking about isotropically emitting bodies. That is, things that are emitting uniformly in every direction. So the other thing this hides, which is, I guess, in the emissivity factor, but it's not only in the emissivity factor, is 2 things, which I'll come back to at the end. One is the temperature is not uniform necessarily of a body, and certainly real bodies don't behave like that. And we can talk a little bit about the factors that change that. And then secondly, this emissivity factor might, if it's a perfect black body, will be 1. Yes, but we know the world is not a perfect black body, otherwise there will be no temperature variations, really. So we're not getting 1, we're getting a variation with wavelength, but we're also getting a variation with structure and with angle. So what starts off as a very simple, we can calculate this, becomes it's a bit more tricky. But it's the foundation of every radiative transfer model that we run, okay? And it's also the foundation of calibration. I don't think I need to go through very much of that. They'll be there in the if you want to read it in the notes. Okay, so now I'm going to use satellites as the illustration. Now remember, if you're sensing from an aircraft, particularly, or a drone, actually you're seeing some part of this. and some parts of this will be very similar. The ground is a bit different. I won't really go into ground, so hopefully you'll see a bit more of that when the other lectures happen. So if you're sitting on a satellite, you can actually basically consider this satellite signal that we see, and I'm just going to talk a little bit about what the satellite signal is in a second, at least in simplicity. It's composed of three components: something that comes up from the ground, from the surface it started, something that originates in the atmosphere, and something that also originates in the atmosphere but also has a component surface. So it's if we're sitting here, if we were outside today, actually radiation is coming down towards us from the atmosphere, and that's being reflected back out, and eventually through the same processes, a small fraction actually gets to space. If we have got a ground instrument looking straight down at the surface, then actually we are seeing that come back into our collecting power. So for the very accurate ground measuring instruments, for example, people do recommend that you measure downwards and upwards at the same time. So even there it has an implication. Just to talk about this and be clear about this for a second, as soon as we start talking about this L term, which is like an energy term, or if you translate to what a lot of people do to brightness temperature, to equivalent temperature from a black body, that LSAT term is already derived. So it's not what a satellite measures. People often say, well, the satellite takes a reading or makes a measurement of temperature. It doesn't. What it does is it has photons falling on a detector, which generates a voltage or current. And people have already intervened to derive for you a level, what we would call in satellite trade, a level 1, which is a calibrated geophysical quantity. So something that's translated to radiance or translated to brightness temperature from these signal detector counts. It's got to have calibration in it. By looking at black body, it will have to have some knowledge of the linearity of the detector. It might have to have corrections for stray light. So most instruments are not perfect instruments. They have some components which are bringing radiation in that we do not expect to see. There's a host of effects that might go on in that. And if you want to do a truly accurate and time measurement, then you ought to trace through all those in a quantitative fashion. Fortunately, we don't have to do that. It's a whole group of people working on that, and you'll hear a bit about that. But for our purpose, I'm going to jump past all of that and assume we have done the perfect calibration. It's almost a physicist perfect case, and we've got a perfect measurement from the satellite, which is this LSAT. So for each channel, we can already expand these terms. Okay, so I haven't expanded this term yet. We can expand the terms here, which we'll come to in a second, and this term here. So let me just talk about this one here. So already you can see that I've introduced two factors here. That's the Planck function for the temperature of the surface multiplied by the emissivity of the surface. So this will be dependent on the material that we're actually looking at, and we'll have a particular wavelength dependence. And it's still a function of wavelength, so each channel, each band that we're looking at. You'll also see that we've got a term here where the radiance coming down from the sky is reflected. And notice that already, I've put that explicitly here, so if I can get this cursor to work here, that the emissivity is 1 minus the reflectivity at that wavelength. So we can instantly replace the reflectivity of that sky radiation by 1 minus the emissivity. And then each of these two terms is attenuating the atmosphere. That is, not everything gets to space or to the plane that we would like to see that comes from the surface. So we have some atmospheric term here, a transmission, which will be between 0 and 1, that says we get lots of it coming through if it's 1, or nothing of it if it gets to 0. And again, I've written something down here about this emissivity in the atmosphere is the same as the absorption, which is 1 minus transmission. Let me try and illustrate that in a second. So yeah, let me illustrate it here. So here is the same picture now of a spectrum. Again, this is an old picture, but the world hasn't changed in radio transfer in all those years. And superimposed on this are Planck function curves for different surface temperatures. Okay, and you'll see a sort of kind of neat thing, which is that where we have little atmosphere attenuation, we see a signal which is more or less close to this 300 Kelvin line. So that tells us the surface temperature is close to 300 Kelvin. We can't say exactly what it is because A, we haven't made any assumptions about the emissivity of the material yet, but we can say it looks like a black body at 300 Kelvin. And we neatly see also actually that at each wavelength, the curves are parallel. So it's not just that it's close, but they're actually parallel, which kind of gives us a feeling the atmosphere isn't making too much of a difference. So we don't know whether the atmosphere is making a difference without doing some calculations, but we expect that from the fact these curves are parallel, that actually it's not making too much of a difference here. So the surface temperature is about 300 Kelvin. But you see, if we measure other wavelengths, we see lots of different temperatures. And in fact, as the atmosphere gets thicker and thicker, principally as we get more water vapor in a clear sky case, then these curves, this curve here, will move away from this black body because the atmosphere is making a difference, even if the surface temperature stays the same. So we get a feel already for the sort of factors we need to think about. Jumping a little bit ahead to other lectures, the more we can explain of this curvature, the more information we know about the atmosphere, the more information we can use for thermal sensing. So we're not restricted just to the wavelengths which have the surface. But currently, we tend to stay at the wavelengths that make the biggest difference. Notice here, if you get out into the far infrared, there's always a difference for this atmosphere. This part only starts to get closer to this 300K curve when you're in the poles where there's much less atmosphere, much less water. And you use a lot of common sense. Tropics, bound to be humid, bound to be a lot of water vapor, worry about the atmosphere a lot more. Go to the poles, very cold, a lot less water vapor, much easier. Lots of other problems. Surface, we'll come to that. Okay, so let me just say, so having said that, let me just go back for, well, actually that all says that. I think the only thing I haven't said here, I'd just like to emphasize at this point, I'm not really going to talk about aerosols and clouds, but first of all, clouds, as you will all know, you can only see in the infrared when it's not cloudy or when you don't think it's cloudy. So already there's a caveat in there. So broken cloud, identification of thin cloud, really very important, very tricky, makes a difference. We can do quite good things now to do that. So we're getting better and better, but still we have to always be mindful of that. I think aerosols is one of the things we don't necessarily still cover well. A lot of aerosols do not affect the thermal infrared in any particular nature. Small, fine particles, the sort of properties of the aerosols roughly go as their diameter and its relationship to wavelengths. If you have but larger particles, they tend to be more effective in the thermal infrared. The biggest, the obvious example is dust particles, desert dust particles. So there's some well-known effects where if you look at the Saharan dust outflow into the ocean, even for sea surface temperature, you could see previously the effects on that in sea surface temperature fields. They were inaccurate because they were actually including desert dust aerosols. Same is true for land. Okay? So you have to always watch that if you live in dustier environments. Okay. Let me just see how we can do for time. Yeah, not too bad. Good. So one blow up of this, just to show you that atmosphere transmission. So again, I'll tend to sort of point to 1,000 wave numbers, which is 10 microns. If you're in wave numbers, then which is the inverse of wavelength, then this region here between 800 and 1,000 is your 10 to 12 microns. Okay, and the reason we tend to have things in wave numbers, if you're a physicist, is actually instruments scale have constant resolutions, often with respect to wave number, not wavelength in the thermal infrared. And actually, all these molecules, their quantum mechanics is linear with wave number rather than wavelength. But that's a detail. So just to show you that there's a very rich atmosphere above us. So although we talk about water vapor, there are actually a lot of gases. So if you have very long path lengths through the atmosphere, then you have to worry about some of these. These gases could be anything from water and ozone, CO2, down to CFCs, and then really obscure molecules that appear in biomass burning and plumes. And we can see all these from space. So that's just to give you a sense that we can actually make really fine resolution measurements. And this is a radio transfer model calculation, just to show you that. Okay, so let me just show you a couple of things then, and to break that down. So again, this is where it gets a little bit crazy, but I'm going to try and go to the simple equation. So if you try to break down the atmosphere term now, which I didn't break down before, in general, you have a quite complicated term. Just look at this one here. But the key thing is that in practice, we can really look at the atmosphere as a single layer with a transmission. So we've introduced this transmission term between 0 and 1. Again, just to give a shout out, don't have to worry too much about this. Sorry, that should have changed to a lambda. Obviously didn't change to a lambda. I'll change it in the notes. If you look at that transmission, it actually is composed of three things. So if you have a path through the atmosphere, it basically depends on how much stuff is in there, how many molecules or particles, that's the U. What the spectroscopy of that material or particles, that's the K, and how long the path is, that's the L. So it looks complicated, actually quite simple. There are three factors that feed into it and give us this transmission factor that we can calculate. All right. So if you're interested in that, you know, talk to me later, or you can read about it. There's plenty of stuff that should give you a sense of it. What I really wanted to get to was this thing here, which is how do we simplify this approach? How do we think about this in simple ways and interpret that diagram that I showed you, but gain some understanding? So here's our signal coming in, and now what we're doing is we're approximating the atmosphere, which it's not, by just one layer of uniform properties. And it's amazing what you can get away with if you do that. You can actually understand quite a lot just from that. Don't do an accurate calculation that way, it doesn't work that well, but you can, you know, conceptually it helps you a lot. And this is one of the beauties I love about thermal sensing, is that if you imagine you've got a signal coming in here from the surface, then what comes out of here is, of course, attenuated by this gas. So we get less out. This transmission goes between 0 and 1. So we can never get more than it in terms of the signal that comes in and its effect in absorbing the signal. But in reality, we can actually get some more signal because this gas has a temperature in itself. And the bit I love about this is that actually you have an extra term. As soon as we go through one layer of gas, we add in another term, which is to do with the temperature of the gas in this atmosphere and the emissivity of the gas, which is related to that absorption, okay, property, and is related to transmission. So this is the simpler expression of it. So you've got transmission here removing signal, and you've got transmission here in effect adding signal, but now according to the temperature of the gas. So you've got the sum of these two terms here. So you still might be a bit confused. Can we look at this practically and see what it does? Well, if the transmission is 1, that is, the gas is not there, effectively it's transparent, what happens? Well, this term disappears. It's 0. And we just get, and this term is 1, so we just get the signal that came in from the bottom, comes out the top. Very nice. Okay, if on the other hand, and this is the curious one, if we can't see the surface, this becomes 0. We don't see the surface at all, but we get this bit coming out because this term is now 1. We see the atmosphere at the point at which it's opaque. So actually, we can get signal coming out even when the gas is absorbing all the signal from the other side. You can set up an experiment like this in a lab. It's kind of fun because in between you get a whole mixed situation, which is difficult to interpret. So if we go to our diagram here now, and this is again an atmosphere. This is the spectrum as we looked at it. This is the one that we looked at before. Slightly different surface temperatures, even less of an atmosphere effect. We're about 320 Kelvin here in our window region. Okay, so here our experiment works very well. Transmission is 1 in our window. If we assume that, then we are seeing the surface. And if it has an emissivity of 1, we've got temperature 320 Kelvin. We don't need any physics. We don't need rate transfer equations. We just need that basic thing. We already know what the surface temperature is. Wow, lovely. Okay, well, what's happening down here? So now we're over the poles. Okay, and now this spectrum doesn't look like this one at all. What was going down is now going up. And the temperature you'll see down here, where there's very little atmosphere, is now around 180 Kelvin. So actually what's happening here is in some parts of the spectrum, generally the atmosphere is warmer than the surface. And in some parts of the spectrum, we're seeing a warmer signal than we get from the surface alone. So some of the traps that you fall into is sometimes assuming that the warmest temperature is always the surface. It's not always the surface. Spatially, if you look, sometimes you get warmer temperatures because you've got a warmer cloud over the top, or you've got a bit of atmosphere that for some reason is very warm. You might have a desert dust intrusion from the Sahara, crosses over Portugal, Spain, and over the UK. Might actually have warm air in it, might be warmer than the underlying surface. So there's all sorts of effects. And that's why we need a rated transfer model. That's why we need some good knowledge of the atmosphere. And Mike will talk to you a bit more about how we, what we do in equations to actually sort that problem out as best as we can. So that leaves us the emissivity term, which is probably what most people are more familiar with. So fortunately, you'll see in a minute, emissivity terms are, to first order, actually show much less variability than albedo in the optical. Okay, so that's the first thing. So that's the fortunate thing. But within the accuracies that we would like to get to for temperature, they are still variable. And I've talked about some of the factors that might make a difference, like structure, the actual material itself. And remember that over the sea, that's the lovely place to do thermal sensing, because the sea does not have a lot of structure. the sea is all water. Even freshwater, saltwater doesn't make too much of an impact, although there is some, and that we need to look at. And the temperature range of the ocean is actually quite small. You know, the coldest temperature before it starts to freeze is around 273 Kelvin. A little bit of play around that. The warmest temperatures are probably the sort of convective initiating surface temperatures, closer to maybe 27 degrees, so whatever that is, about 300 K. All right, so you've got a narrower range of temperatures. So when you do that over the ocean, even with 2 channels, you can get down to accuracies that are around the 0.1, 0.2 Kelvin. If you put in the 3.7 channel, which you can also do at night time, then you really are, you know, when we do biases against lots of observations, I mean, the difference is immaculate. I mean, it's so small, it's untrue. Okay, so sea is a perfect example of what we can do. Luckily, the oceans are 70% surface, brilliant. Unfortunately, we live on the 30%. That's much, much more complicated. Okay, so and when we get those complications, there's a couple of things then. So one is the emissivity factors become much more complicated. So on the along track scanning radiometers and similar instruments, we can use this multiple view angle to really add to that nice calculation. Remove the atmosphere, we've got a well-defined surface. Actually, the ocean doesn't vary very much spatially either, not at those levels. There is some variation, and you can calculate that effect, but it's not big. When we get to land, you know, you walk outside. If you walk into the park, you're going to have a completely different temperature from a path to the parkway to the water next to it. The classification, the identification of material is really critical, or the ability to derive the emissivity simultaneously with the temperature is really critical. And we'll talk a bit about algorithms in future lectures. And the other thing that matters a lot is the fractional vegetation cover if we're away from buildings. I should have put buildings in here. Sorry, it's buried in surface type. So buildings matter a lot now for us, especially as we head towards urban sensing. But in the Western world, of course, we have buildings everywhere. I mean, one of my students is doing an optical calibration against the crowd with aerosol and surface reflectance. You know, and there's different types of fields. There's buildings in the field of view of the satellite instrument. You know, you can't get away from that. But also, even where we just have vegetation, where we have to worry about how much vegetation, we might have to worry about what type. But also, we have to worry about the other factors that might change emissivity: soil moisture, as well as the soil itself. How wet is that soil? It might even be that it's the whole crop or the whole forest if it's just recently rained. If you live in the UK, we have actually terrible observations if you stick to one local time. But if you can vary the local times, actually you probably do much better. So today it's a bit grey, tomorrow it'll be sunny. Brilliant. But if we catch the cloud free just after the cloudy rain, what difference is that making to our emissivity? We just have never really got to the grips with that. There's lots of stuff that we need to do there. So brilliant, but you know, not as good as we would like. Let's show some pictures of that. So again, some of you might be very familiar with this, but this just shows albedo on the surface and emissivity now translated to scale. So worldwide, we can use databases to look worldwide. So you can even put in your location. You could get an emissivity estimate. Do we trust them? Not that much, frankly. I think there's a whole world, and you can see already. You know, I think that's our third challenge that hopefully you've already picked up is, I think, emissivity and calibrated emissivity measurements in lots of different environments. It's an international challenge because you can't just do it in one place. All right, so really is a big challenge. That's because as a function of wavelength, you have dry grass here has structure. Fortunately, at 10 to 12, it's not that big. But again, how many times do people assume that signal is the same? If you look at, sorry, that was in reflectance space. Better to look in emissivity space. You can see it a bit better here. But even over here, 10 to 12 microns, you can see variations in emissivity. And what's more, that emissivity is not necessarily constant between different channels. So you can't assume. You can postulate, you can estimate, and you know, a way around this, which we do, is you estimate the differences and say that's part of your uncertainty budget. So there are things you can do, but it's, you know, in reality there are things that you need to do. And then as soon as you get into materials, again, that 10 to 12 micron tends to be nice, but as soon as you get towards the 8 microns, and of course, unfortunately, a lot of this is from a satellite point of view is restricted, but actually for plane and drone and ground remote sensing, it's possible that you can use this region here to help better characterize those materials and get that complete emissivity spectrum. And you can see this is the ASTA spectral database that I've been extracting plots from. You can see here that we've been really trying to get, at least in the laboratories with our JPL colleagues, complete spectral coverage. Not really got the time to talk about it here, but our King's colleagues, and you can ask Martin Worcester about this tomorrow if you have time, have been trying to conduct an intercomparison standard measurement of emissivity in different laboratories. And lo and behold, guess what? They don't agree. So even in the laboratory, we don't agree on accurately what is the emissivity for a particular material. And that material is normally being translated from the field, so it spends a certain amount of time in transit, etc. So there's a whole new can of worms there as well to unpick before we can go forward again. Okay, nonetheless, I don't want to be too, completely pessimistic. So nonetheless, we can, with all that skill, and and you'll see that in some of the lectures, come up with land surface temperature. I've mentioned that the issue of local times. This is global land surface temperature, from the ATSRs, but this will be at 10:30 combination time. I think this looks to me like a daytime image, so it'll be 10-ish. We vary the times, but even there we have problems. So you have satellites, and for various reasons, they don't fly at the same local time as its predecessor. So half an hour can make a difference. So luckily, we have geostationary satellites now, and actually the latest geostationary satellites are really going to be an improvement, provided we can get their calibration right, because they are going to be measuring, in some cases, more frequently than every hour, even every half an hour. We might, in some cases, step down to, as you do with Himawari, every 10 minutes or so. But at reduced spatial resolution. So you see that system's really begin to change, but that's, that challenge coming up. We're trying to go to higher and higher spatial resolutions. And this is an ASTA. This is a Japanese satellite. I've mentioned this a couple of times. We like ASTA, not only because Mike's trying to finish a paper on it, aren't you, Mike? But because it has this multi-channel approach. It actually has 5 spectral channels to do land surface temperature. So we can apply algorithms to get the temperature and the emissivity at the same time. And it still is high enough, even at sort of towards 100 meters, that you can get the signatures of intersections of urban green space, of riverbeds, dry riverbed noted in there, of airports, etc. And you can see at quite fine scales here. So this is the optical. In here, you can tell the difference between irrigated fields and the non-irrigated fields very nicely in here. And again, many of you will be familiar with this, but trying to do it from a range of systems in a trusted and high quality approach is the challenge for us. I talked a bit about emissivity. So here now I'm really into the challenges. So you've understood the emissivity challenge already. The one thing that I haven't brought out, I mentioned at the beginning, that I want to just go back to is this angular question. So this is again where ground sensing and satellite sensing really have important roles to play in how we interrelate these things. Dare I say it, the natural state, the vegetated state is perhaps the easiest to get to. The urban state is probably really hard in terms of fractional cover, sky view factors, and all the rest of it, canyons, etc. But even in a simple approach, it's the fact that emissivity varies as a function of angle. Now, if that's been taken into account in the algorithm used to provide the LST, that's a step forward. So that might have done it to greater or lesser extent, but hopefully the uncertainties arising from doing that are smaller. But then we come up against that other bit, which is the temperature itself may vary. Now, I haven't put a picture in about that, but just to emphasize that again, particularly in the daytime, but it could also occur in the nighttime in cooling. In the daytime, the most obvious influence is the sun and its heating effect, right? So the sun's going to be on one side of your object, and it's going to heat that side preferentially, depending on the absorptivity of that material. So we instantly have a question about which side of the material is absorbing. If you look at the geostationary sensors and you try to compare them with the EOs, I'm not really up to date with what we're doing this year, but in the last couple of years, we've seen some quite noticeable directional effects around that. So plenty to overcome here. And then I wanted to close here, if I could, on the last challenge, which I'm just going to illustrate with sea surface temperature, because I know a little bit more about that. So we've mentioned here just the thermal infrared, but of course, we've also noted quite a lot of interesting challenges, let's call it that way. And one of the biggest challenges is cloud, right? So what we really love, of course, is to have a sensor that wasn't affected by cloud as much. And to do that, you would go to the microwave. Now, the problem with microwave, and I've got a slide that talks about it, is really spatial resolution and the way it works actually, because it has side loads as well. You can just see the name of it, side load. But there's some interesting questions to ask about whether, and again, this could be a ground thing as well as a space thing. If you could do this, what information would you actually get from it? So, as always, you get the pros. We would get a measurement in cloud and a measurement in the clear sky, and in clear sky case, we could compare both. Brilliant. We'd be able to see how temperature vary between cloud and clear sky. That's a huge thing with climate models, indeed with many models, which have to operate in all conditions. What are the cons? Spatial resolution. The emissivity. Well, hang on. I've forgotten about that factor. The microwave emissivity is even more complicated than the infrared emissivity. It depends on the polarization of the wavelengths as well. And also, it actually turns out that you're measuring a different quantity. So on this graph here, and notice the scale is really very thin, but could be crucially thin and important. The red, so a grey would be, I think, the true skin, that's right at the top of a bit. But even within microns, the infrared is very close. But you can actually see a small, and for land surface temperature is really small, but for sea it matters. You know, small temperature gradient between the very top and where the infrared sensor is sensitive. If you look at the microwave, you see a bigger effect. Now in land, that is interesting because actually you're getting some penetration of the microwave actually into soils, and then the scattering of microwaves with vegetation and tree structures and buildings is just a who knows. Okay, no one's managed to do it successfully. So just to point out, there are some values, but also some interesting research challenges around doing that. Just in here, I won't dwell on this, but I put in some of the pros and cons. At the current time, you know, for a lot of the work we want to do, thermal infrared is still by far the best way to do it. And one of the reasons is when we do it well, and when we visualize it well, and I think you've got a visualization session as well, if I recall correctly from the agenda. You know, it's how we present that information. We are finding that there is an incredible outreach around thermal sensing as well. So this is a picture that ESA created. This is Glasgow, if you don't know your Scottish towns and cities. You might actually guess why we did this image. COP26 was in Glasgow, and so this was an image we created from land surface temperature measurements for that. Well, ESA created the image, but it was our data. So we are making progress, and we are finding that in our science and discovery centres, they are constantly asking us now for projections. We're working with our mapping agency, the Ordnance Survey, to see how people would use temperature data mapped onto their interfaces, because it's much more accessible there. So our other challenge is not just having it ourselves, giving it to other people in a way that they can use. So let me just close. So I think the great news, despite all of that, is that actually I think determination has advanced considerably in recent decades. Lizzie Good, who's going to talk to you on Wednesday, I remember when she was doing her PhD work, probably 15 to 20 years ago, it was really around sea, but we said, well, actually land, you could do a bit of land. And Lizzie did a very stretching PhD to her credit, did some land stuff as well. We were really just getting into that stuff as a community then. And we've moved hugely on now. It's now declared as an essential climate variable. We've written the specs around that. We're achieving some of those specs. We're really hitting the challenges around agriculture, around urban environments, because there is not the information otherwise that people can use. I hope you've got the impression also, though, of where we need to take care, where we need to work hard together, where we need to maybe see some real research challenges for future work. And that's around those algorithms for the high accuracies, how we connect data sets spatially and temporally, how we think about anisotropy, that is the non-uniform behavior of our surfaces that we're looking at, and how we bring together those multiple high-resolution sensors with these high-accuracy LEO and GEO sensors at other spatial resolutions. So just a few things to talk about during the next few days in the week. So I'll stop there. Thank you. Might even have time for a few questions. Yeah. Yeah. Yes. Yes. What work is done?
Sorry, I'll repeat myself.
Yes, that's fine. Thinking time.
Yeah. So users are primarily interested in daily land surface temperature as well as its diurnal variation.
Yeah.
Given the fact that you have polar platforms only happening twice a day, yes, you have geostationary, but at fairly low resolutions at the moment.
Yeah.
Is anyone working on trying to do interpolations using NWPs to actually provide missing information for those 2/3 of the days that are covered in clouds?
Very good question. Yeah. So first of all, just to say, yeah, that time series bit hits us hard. We're on that EO Data Hub project I mentioned in the first welcome talk. One of the things we're doing is trying to give people some representations of surface temperature, because if you look at climate projection models, they are also spatially limited, less so than they were. So UK, I don't know what happens in other countries necessarily, but in the UK, we run a special climate projection model, well, the Met Office do, and that's about 2K by 2K to 12 by 12, depending on what projection and what you want out of the model run. Okay. So we're trying to provide, but even at that scale, we know there's finer thermal information. So we want people to have access to that. But then you run up against exactly this problem. How do we even represent what is a snapshot against what is a dynamic changing? So we've done some things there that try to represent seasonally. We've also tried to look at, just from the observations, how do you develop time series with multiple satellites? So obviously that's getting better at the current time. So if you think you've got SLSTR, you've got MODIS VIIRS, you've got AVHRR Meta-Marge on the Met Office, right? But you still can't beat the clouds, okay? But you can use the multiple observations to give you more time. Again, I think there's still huge challenges even to do that. So then the question is interpolation. So for me, the ideal way to do that would be to have a weather-driven interpolation, right? So that the forecast model or the nowcast model provides you the weather conditions around which you fit the LST data to that in some way. The problem, I think, with it still, and it may actually work, but the problem I think with it still is that in models, people talk about surface temperature, but in models, at least in atmospheric weather models and climate models, when they talk about surface temperature, what they actually mean is the air temperature, the 2-meter air temperature, not the surface temperature. So now we've got this other bit, which I didn't talk about here at all, which is air temperature, surface temperature. Lizzie, who's coming here on Wednesday, is that's one of her areas of research. So yes, I think we're looking, but are we there? Probably. Are we anywhere near there? Probably not. And I think that is a real challenge for us. So yeah, sorry I can't give you a better answer. Yes, people are working on it. No, we've got a long way to go.
Thank you.